continue our technical discussions. So this is a new section. So we are moving towards the emerging memories. So far we have talked about the mainstream technologies like SRAM, DRAM, Flash. And starting from today, we are going to move into the new technologies. And you have heard from Henry about those potential market of those technologies. But today we are going to talk about the technical aspects of those emerging non-volatile memories. So this is the outline. We will talk about a few emerging non-volatile memory candidates, and then we will talk about the array architectures and the design considerations for the array architectures, because we may have some problems when we use those devices. So in particular, we are going to talk about the crosstalk, the sneak path, and then we will discuss why we need the selector devices. And at the very end of the section, we will briefly talk about the 3D exponent memory from Intel and Micron. Okay, so this is a recap of the memory hierarchy we have learned before. And you know we have different technologies serving at different levels in this hierarchy. And due to the different latency and the capacity, the trade-off between the latency and capacity, the different memories serve different levels. And there is a boundary here between the main memory DRAM and the flash-based SSD. So this is the boundary between the volatile and non-volatile. And then we do see the gap in between, in particular between the DRAM and the NAND flash. There's gap in the latency and the capacity. So that motivates the industry to look for the emerging non-volatile memory to fill in that gap. This is for standalone memory application. But as Henry also mentioned that there's another small market for the embedded memories. So then there is also a need to look for the emerging non-volatile memories that are compatible with the logic process if we can scale that down to beyond 28 nanometer. So the scaling of the traditional memory, like SRAM, DRAM, Flash, is facing the limit. Of course, the innovations are still going on to make, for example, 3D NAND Flash. But if you only look at two-dimensional space, those technologies are facing the scaling limit. And what makes an ideal memory, right? So here we have a list of the attributes, or let's say a wish list for the ideal memory. And for example, you want the memory to be non-volatile, right? So you don't need to power on when you are in the standby mode. And of course, high density, as small as possible. No power consumption for the read or write operation. And then bit addressable. So this is respect to the NAND flash, you have to do the block erase. So ideally, you want each bit to be individually accessible. So direct write without prior erase. This is also respect to the flash, NAND flash. Endurance, right? How many cycles you can write or read. And of course, no cost, no multi-year supply to be compatible with logic. Because NAND flash, you know, like 10 volts, very high. So scalable to like below 10 nanometer, compatible with the silicon CMOS fabrication. So you can fab that in the foundry. So those are the ideal characteristics for the memory, but none of the memory can satisfy all of them at the same time. So you have to do the trade-offs. And let's look at what really makes a memory. So basically, you are looking for some physical properties of the material to have some hysteresis. because you want to keep memory state for a single, let's say one single level cell, you just need 0 and 1 state. So you need some state. So that means you need some hysteresis in the physical properties. And for the conventional memory used in the mainstream technology, like SRAM, DRAM, flash, actually all of them can be regarded as charge storage mechanism, because no matter which one, you store charge in some places in that memory cell. For example, for the SRAM, you store the charge in those two storage nodes. Those two storage nodes, of course, will have some parasitic cap, like the CDB, CGD of those transistors associated with that storage node. You store the charge there, essentially. DRAM, of course, you know, a cap, right? DRAM cap. So you store charge there. Flash, where do you store the charge? Floating gate, right? Or the, if it's trap, charge trap cell, then it's in that nitrate layer. So you store charge somewhere, essentially. So those are the charge storage mechanism. However, there are some other physical properties that you can store the data. So those belong to this emerging memory, and many of them actually are resistance-based. So you store the state in terms of the resistance of the device. There's different kinds of mechanisms to change the resistance of the device. So here I list a few, like phase change, filament formation, spin torque, transfer torque, spin orbital torque. So we will discuss those in more details in the later individual sections on those emerging memories. There are different mechanisms to change the resistance of your device. And you can think the resistance, let's say high means 1 or means 0. Resistance low means 1. So you just use resistance to represent your data. And that on other kinds of mechanisms, ferroelectrics, you have learned this before. So essentially it's a cap. And there's some mechanical based memory, which is very slow, but it's doable. So if you you can make some nano electrical mechanical relay, then you can basically have 2 electrodes, and then they touch, then you have conduction, and they break, then you don't have conduction. So you can use that to store the data as well. So due to the mechanical contact. So here is the scaling challenges for the conventional charge-based memory. And so as we discussed, no matter which one, they store the charge in somewhere in this memory cell. But as you scale the technology node, so the storage for those charge, you need some space to store the charge. So that space is scaled. So that means you fundamentally will have the limit number of charges you can store in those space. So that's becoming the challenges for the scaling. So many of those previously discussed challenges are associated with the scaling of those space for the charge storage. And resistive memory. So as I discussed, there are many mechanisms to change the resistance of a material. So if you do that, then the memory cell will be based on the resistance, or sometimes we call it resistive memory in general. So we need a mechanism to change the resistance of the cell or the material of that cell by electrical input. Okay. For example, we can apply voltage or current to that cell, and then we can change the resistance. So many of the mechanisms here are associated with the atomic arrangement of that, rearrangement of that material. So we will discuss the popular emerging technologies at a very high level in the next few slides. So here is just to the very high level, big picture, and in the later sections we are going to have individual technologies to be discussed in more details. But today I just give a very high-level overview of each of those technologies. So the first one is called the STT-MRAM, Spin Transfer Torque Magnetic Random Access Memory. So this kind of device is based on magnetic material, and sometimes it's called spintronic devices. And the basic structure is made of this MTJ, magnetic terminal junction, and the basic structure is something like this. So you have two magnets. Typically, the material is this cobalt, iron, boron. So this kind of material is little magnets, and they are separated by oxide terminal barrier. And in many cases, in this MgO material, it's like 1 nanometer thick. So the basic mechanism for this device is to tune the magnetization, the polarity of those two layers. And here we have the pinned layer, which means the magnetization polarity always pointing to the, for example, in this example, to the right. And then we have a free layer here, which you can tune the magnetization polarity, left or right. Okay. So by writing the data into this memory cell, you have two configurations. One is the parallel configuration. That means those two magnets will have the same polarity. Okay. Polarity means you can think it's North Pole, South Pole, right? Magnets. So they have the same polarity. And the other configuration is anti-parallel. That means the top one is switched to the left, and they are in anti-parallel. And the result of this two configuration is that the resistance across this device. Let's say if you pass current through this device, this current will give you some resistance if you have some read voltage. So this resistance will be different. If the device is in the parallel state, the device will have lower resistance than the anti-parallel state. So here the R parallel smaller than R anti-parallel. So you can think the R parallel is on state, or is one state, and this one is 0 state. So the resistance difference in this kind of device is not very large. The on and off state maybe only have 2 times difference in the resistance. But still you can sense that small difference through your sense amp. Okay, so this is the first technology. And the second one is called the phase change memory, PCM. So this one depends on a particular material called the phase change material. And in many cases, it uses chalcogenide material. Chalcogenide is a material in group 6. So if you look at the periodic table, in group 6, first you have oxygen, and the rest will be in this so-called chalcogenide. So like the antimony, tannarine, so here. So those are the chalcogenide material. And the typical composition is this germanium, antimony, tannaride 225. So this is called GST material, GST. And this one is a basic building block of the 3D X-point technology that Intel and Micron invented. So it's based on this. So the mechanism for this one is to change the phase of the material. So the phase means the atomic, let's say, arrangement. So let's say this is the lattice of the atoms. And if the atoms are in this ordered, or let's say very regular configuration, this is called crystalline phase, like crystals. If the atoms are in this kind of very regular ordered configuration. But if the atoms are kind of random in the location without this order, then it's called amorphous state. So the mechanism of this device is to change the material between the crystalline and amorphous states. And if you do that, then you will find the crystalline phase resistance will be smaller than the amorphous state resistance. So how do you change between those two states? So the typical way to do that is to apply heat. So the crystalline material will melt when the temperature reach certain melting temperature, typically hundreds of degrees C. And if you melt the material, you know the atoms can move around, so they no longer maintain this regular phase. So then the atoms move around, and then you do a so-called quench process. That means you remove the heat very quickly, so the atoms will remain at those random locations. They don't have time to rearrange. Okay, so it will be left at that quenched state. That will make the material become amorphous. Okay.
Since this has already been used in 3D crossmatch, so did 3D crossmatch have higher energy consumption than 3D NAND?
Yes or no. So at the cell level, yes. So you need to, I just said, apply heat. But of course, in the circuit, you don't have heat to apply. So what you do is to pass current. Use Joule heating, right? You know, current, I square R. You have the Joule heat. So you need to pass much current. So in that sense, the write power is high. But the problem for the NAND is that you will always do the block kind of operations. So you have many unnecessary kind of charge and discharge for the whole array. So in that sense, NAND flash also consumes much energy. But for the cell, yes, this one definitely is larger. And this is the GST based on phase change memory, and mechanism is to change the phase from crystalline to amorphous. And if you want to change from amorphous to crystalline, then what you do is to apply lower temperature, but for a long time. So basically, you recrystallize the material.
Professor,
Mm-hmm.
what sort of times are they talking here to recrystallize?
Maybe tens of nanoseconds to 100 nanoseconds. The quench needs to be very fast, like below 10 nanoseconds.
So do you use this as like 0-1 binary representative, or can you read the voltage out of this, like an analog computation?
Yeah. So we will discuss that in more details. For all those memories, not all of them, let's say. The STDM RAM is just 0 and 1 because the on-off ratio is so small.
Yeah.
So it's only 2. So it's very hard to distinguish already. So you cannot have more levels.
Mm-hmm.
and like flash, you have many levels, right?
Sure.
So the phase change memory, yes, you can do multi-level. So you can tune the resistance because on-off ratio is kind of large, maybe 100 or 1000. So you can have many levels in between the very high and the very low states.
I see.
So yeah, this is doable. And then the third one is this called this resistive random access memory R1, and in many cases this is based on some oxide material, and I mean nominally oxide is insulator, right? So it's high resistance. But when you apply some voltage, when the oxide is very thin, like a few nanometer, you can somehow break down the oxide. So basically you create many oxygen vacancy. You knock out the oxygen atom from the oxide lattice, and then you create this filament based on the oxygen vacancies. And then the current can flow through the filament. So it's like a conduction path between two electrodes. Then you have the on state. You have low resistance. And then if you reverse the voltage polarity, then you can recover this kind of oxide partially by rupture this filament, and you have some gap in between. So then the turning current is small, so you go back to the high resistance state. So this is the general mechanism. So you need to know that the low resistance state is due to the formation of this filament, and high resistance state is due to the rupture of that filament. And the different kinds of the R1 are two subcategories. One is that this is called oxide run. So this is when the filament is made of this oxygen vacancy. And the other one is called CB run, conductive bridge random access memory. In this case, the filament is made of the metal atom. So in this case, you need to have some active electrode, for example, copper or silver. Then when you apply large voltage here, you can drive the copper or silver atoms into the oxide. So they will form this metallic bridge between the two electrodes. So you can pass current. It's like you short those two electrodes. So then you will have current. So no matter what, this is based on the formation of the filament in the insulator. In many cases, oxide between two electrodes. Okay, so this is a quick summary of those three resistance-based emerging non-volatile memory: STT-MRAM, phase change memory, and R1. So here we just consider binary states 1 and 0. This is so you can read this. 1 and 0 is based on what physical properties, like this anti-parallel, parallel magnets. This one crystalline amorphous phase, and this one is the formation or the rupture of the filament between the two electrodes. Okay, so let's look at some of the AV characteristics of the resistive memory in general. So there are two kinds of switching mode. One is called unipolar, one is bipolar. Unipolar means that you apply the same polarity of the voltage to change the state. For example, here, initially you are at the red curve. That means you are in the high resistance state because the current is small. And when you apply some voltage to here, then the device can switch from the high resistance state to the low resistance state. And then when you reset the device from the low to high resistance state, you apply the same voltage polarity. That means also positive voltage here, and then the device can switch from the low resistance state to the high resistance state. And phase change memory is this kind of unipolar operation. You only need a positive voltage to switch it. But as I said, so you need to apply different kinds of magnitude for the reset, which is from the crystalline to the amorphous state. You need to pass large current, like here, large current to hit the device. to some temperature locally, and then you quickly withdraw your voltage, so the device will quench to the amorphous state. So the other mode is this bipolar mode. So for this one, you need to switch the voltage polarity to switch back and forth. For example, if initially the device is in the high-run state, HRS, short for that, and then you turn on the device, set the device from high resistance to the low resistance state, so then the device will in the low resistance state. But when you need to reset from low resistance to the high resistance state, you need to switch to the negative voltage here, and the device will switch. So you need the two polarities for the electric field. So this is to switch the device. Of course, later when you read, you will apply some voltage here. This will be your read voltage, right? So then this read voltage will not change the state, and then you can distinguish the current from two states. And then your sense amplifier will tell, okay, this is 0, this is 1. So STT-MRAM is this bidirectional, bipolar mode, and most of the ARA devices also bipolar mode.